Hello everyone, in this video we are gonna find the deflection of the beam under both point load and distributed loading. So the equation for deflection is y double prime mx ie. That means that the first step is to find the moment. Because the load changes at point B, we have to make a section cut here, we call it section cut 1, and then another section cut here, we call it section cut 2. So let's start with the first cut. So our first cut would be at x somewhere between 0 and a, and I'm gonna keep the right side. The reaction force, we can find the reaction force, but for our case I'm just gonna call it R1. I have my distributed loading, and here I have my moment. I'm gonna call it moment 1. The resultant for my distributed loading would be W, because this is X. That would be WX. So summation of forces, or summation of moment, at point C, I'm going to call this point C, would be 0. I assume counterclockwise to be positive. This force is creating a clockwise moment about point C, so that would be a negative value. I will write negative R1 X minus the WX is creating a positive moment because it's counterclockwise, and the moment arm is x over 2, so positive WX x over 2, and our moment itself, which we drew it in a counterclockwise, so it would be 0. So at the end, if I rearrange it, M1 would be R1X minus half of WX squared. I put it on the other side. And that's for first cut. That's for this condition between 0 and A in this region. Let's do the second one. For our second cut, I call this second cut. That would be for when X is between A and L. I keep the right side of the beam. I have R1. Again, I have the distributed loading. I have my X. The moment, I'm going to call it M2, this point. And I have the force F that acting somewhere here. And the distance to the force would be A. I'm going to write summation of moment about point C. Again, let's call it C2, so we know that section cut 2 is 0, counterclockwise is positive. R1 again, creating a negative moment, clockwise moment, the moment arm is X. W, again, the magnitude is WX, the moment arm is half of X. So nothing has changed so far in that term. And it's creating a positive moment because it's counterclockwise. The only component that I have is F that is creating a counterclockwise. So it's positive. The magnitude is F. And the moment arm is this distance. Let me show you by another color. Well, let's choose red. That would be this distance. This distance is simply X minus A. So X minus A plus M2 equals 0. So if I rearrange, my M2 would be R1X minus half of WX squared minus Fx minus A. So if you just compare, the first terms are the same, the second terms are the same. This one has an additional term. So after A, we have an additional term. So we have two moment equations. That means that we can get two deflection equation and two slope equation. There is a way to combine all of them together, but for now we can proceed with one. So let's say y double prime again is 1 i.e. mx. Because we have two m equations, we have to call it y double prime 1 and m1. Then y prime 1 would be take an integral of this guy, so m1 r1x. That would be r1x minus 6wx cubed plus c1. And if I do y1 would be i.e. r1x wx 24 plus c1x plus c2. And these deflection and slopes are true from 0 to a. Also, I have y double prime 2 that is related to my second moment. So if I want to find the slope, I and E are the same because the shaft is made of the same material and diameter is not changing. The first components are the same. Just the last component would be different. Plus C3 because C1 is no longer available. We do C1, C2, and this constant would be different. So we have to name it a separate constant, C3. And if I want to do the deflection, I take another integral. R1x cubed 6wx to the 4th 24 minus x minus a cubed 6 plus, so pay attention to this, c3x plus c4. These are my slope and deflection based on the two moments that I have. Now it's time to find integration constant, C1, C2, C3, C4. We have 4 integration constants, so we need 4 conditions. What are our conditions? 2 of them are obvious, the other 2 not quite. We can say that at x0, y1 would be 0, and at xl, y2 would be 0. At xl is the second part, that's why we use y2. The deflection at the two ends of the beams are 0 because it's simply supported. That's not enough for us. We need 2 more conditions. Here we don't have boundary condition, but we call it continuity conditions. Means we don't have a jump when the section changes. So at x equals a, the slopes are the same regardless of whether we are using equation 1 or 2. And again, at x equals a, the deflections are the same. So now I have my 4 conditions to find for the 4 integration constants, C1, C2, C3, C4. That's the first step, that's the first method for these beams with 2 different loadings. But the second method might be even easier, to combine the moment equation. We said that the only difference between the two is the last term. So if I have my moment equation, I had R1, let's bring it up here. I had R1x minus half WX squared, and then I had the other term, 1x minus half, and this was the term that would appear for the second segment and it would disappear for the first segment. Maybe I can use the convention to use that. So mx r1x minus half wx minus f, and I'm going to use a notation. We call it broken parentheses, or we call it a macaulay bracket. So this is a broken parenthesis. What does this one do? Let's look at x minus a. X minus a would be 0 if x minus a, this term, becomes negative. Or in other words, if x is less than a, if you are in the first segment. And it becomes a normal parenthesis. When x minus a is bigger than 0. Or x is bigger than a. We call this broken parenthesis. Macaulay bracket. So when we are now taking a slope equation, we don't have y1 or y2, we just call it y prime and take an integral of our equation, r1x minus x over 2 6wx cubed minus f x minus a 2 over 2. We keep it as this one, and then when I want to find the deflection, I do the same thing, just in our notation use broken parentheses. These are broken parentheses, are different than normal, and we know this term would go away when this one becomes negative. That way I have reduced 4 equations to only 2 equations and only need 2 boundary conditions that we discussed. So even in MATLAB, understands broken parentheses. If I want to put this in MATLAB and write this in MATLAB, I can write f times x minus a. I have 3, and then I have here 6. That's fine. Just to say that this is a broken parenthesis, I need additional term multiplied by x bigger than a. That's it. That's the notation I use. That's the extra thing that I need to put into my code to tell it this term would go away if this condition is not met, if x is not bigger than a. If x is not bigger than a, I don't want you to use a negative value here. I just want you to get rid of the whole term. And that's what MATLAB does. That's the power of broken parentheses. Again, if you look at the if condition, if x is less than a, here we are not going to have put a negative value because that would set our equation incorrectly. Just get rid of this. That's the difference between Macaulay bracket or singularity function and a normal parenthesis. It reduces our equations.